Dear participants, welcome to third Make a Difference in Education Summit, which we hold via online platform due to pandemic. In this summit, we aim to provide you innovative and different perspectives. Now, Professor Edward Frenkel, who is a professor of mathematics at the University of California, Berkeley, will be with us with his seminar, Imagination and Knowledge. We request you to mute yourselves during the speech. If you have any questions during speech, you can reach us via chat box. This session will be recorded and streamed on YouTube. We wish that you will have an efficient seminar. Now, Professor Edward Frenkel will move on with his speech. Okay, you can begin whenever you want.
All right. Well, hello to everyone. Good morning. Well, it is morning for me. It is 9 o'clock in the morning here in California. And I imagine for many of you, it is evening already, Saturday evening. So
yeah,
thank you for coming and deciding to spend some time with us this evening or morning. Isn't technology amazing that it enables us to connect like this? So I would like to, well, first of all, I want to say it's a great pleasure because I want to thank the organizers, first of all, for inviting me. But last time I was in Turkey was about 5 years ago, was in December of 2015. And I spoke at both METU, Middle East Technical University, and at Boğaziçi University in Istanbul. And both lectures were perhaps some of the most memorable lectures I have ever given in my life. So the warmth of the reception and the interest that was shown by the audience was really incredible. And it stayed with me in my heart. So it feels like a nice return, even if in a virtual format, but it's a nice return to Turkey, which is one of my favorite countries. I love visiting Turkey. I have many friends and so on. And I look forward to visiting again in person. But for now, we'll do it in this way. So what can I tell you today? So it's also great to be part of this education summit, because I think education is really, well, the world, as we know, has a lot of problems. But I would say maybe education is really the first one to focus on. And this is where I think we can all make big inroads into tackling the world's problems. So, but before I begin, I just want to see something, because I'm not sure that it is being shown, because I have told many of my followers to see me on this YouTube channel, but I don't see it anyway. So if somebody who is doing technical issues is aware of this, I hope you guys will fix it. Anyway, back to my talk. So this is what I want to talk to you about. How do we instill knowledge in our students and give them the tools that they need to navigate this brave new world, which is so fast and so, governed by technology, but at the same time, preserve their natural sense of wonder and sense of awe and mystery. So I want to start. Let me share screen. There we go. I hope you guys can see it.
Yes, we can see.
Okay, great. And so this is what I want to begin with. Albert Einstein. I want to talk about imagination and knowledge. And so Albert Einstein has said, imagination is more important than knowledge. For knowledge is limited, whereas imagination embraces the entire world, stimulating progress, giving birth to evolution.
Ne yapayım? Şu an Edward Bey'in sunumundayım.
Probably there was a problem with microphone.
Oh,
You
okay.
can continue.
Knowledge is limited, whereas imagination embraces the entire world, stimulating progress, giving birth to evolution. It is, strictly speaking, a real factor in scientific research, you see, imagination. And he said also, I believe in intuitions and inspirations. I am enough of an artist to draw freely upon my imagination, you see. So I was really, when I first read it, I was really puzzled because, you know, Einstein is an icon of a scientist. And you would expect the scientist to be on the side of knowledge and to say, okay, you have to learn and you have to learn more and so on. And here he's actually saying something opposite, right? So he's saying intuition, inspiration, imagination. What does it mean? So even for a scientist, it is important. Huh? So even for scientists, it's not important. It's not sufficient to be surrounded by books and just pouring over those books and going over that knowledge. There is something more that you need. There is some spark that you need. And so I was wondering about this, and I asked myself, where can I see examples of this type of approach of imagination in the history of mathematics? Okay. And so the first example I want to give you has to do with a great Italian scientist, mathematician, Gerolamo Cardano. Was not only a mathematician, was also a physician, a scientist, also an astrologer and a gambler. It's a fascinating story. 16th century, okay? And so in mathematics, he's famous for his book called Ars Magna, the great art, as you can see here, the great art of rules of algebra. So you call them rules of algebra. So 16th century, one of the main books of the early Renaissance. And so, by the way, I want to mention that these days, if you Google Cardano, this is what will come up. It is one of the most popular cryptocurrency networks these days. I don't know if you know about this. So this is a chart which I copied yesterday. It's been it has a great run so far this year for crypto enthusiasts. I love it actually always when a mathematician is given respect by naming something in the financial world after them, say. And this, of course, brings to mind something that you guys have seen many times. That's the 10 lira banknote. I don't know actually if it's still in circulation. I hope so. I wonder if you ever wondered who it is on this banknote. It is a mathematician, Dr. Jahid Arf, who was a professor actually at METO, at Middle East Technical University in Ankara. And he has made many important contributions to mathematics, including the Arf formula, which you see displayed on this banknote. So it's a nice reminder that mathematicians are important. Okay, so back to Cardano. So Cardano was the first to theorize imaginary numbers. You see, imagination. And the point is that what are the imaginary numbers? So for example, square root of -1. It doesn't exist as a real number because we want a number whose square is -1. But everybody knows that for a real number, the square is positive or 0. Right? And so that everybody knows that such numbers do not exist. Square root of -1 or square root of -n, where n is a positive number. They just don't exist among the real numbers, among what we used to call the real numbers. And we thought those were the only real numbers. But Cardano went further. He did not allow this preconception to stop him. He imagined these numbers. And guess what? He was able to derive some important properties, not only of these numbers, but also real numbers. Here's what he wrote. You have to imagine specifically square root of -15, he wrote in his book. Putting aside the mental tortures involved. And I love this quote because you remember when you were studying mathematics. So many of you are perhaps still studying mathematics. I consider myself a student of mathematics too. And mental tortures is something I go through every day, because when you do science or mathematics and any investigation, You have to think about, you have to concentrate, and you don't always understand. In fact, most of the time you don't understand, at least I don't. And that gives you the sense of torture, of mental torture, that you have to overcome, you see. That's the effort, that's the real effort. And so he said, but let's overcome our mental tortures and let's follow our imagination, right? So that's what he did. And he came up with this numbers. And now, today, so this is only 500 years ago, basically, less than 500 years ago. This was such a mental torture. Even 100 years ago, let's say, people would be very, wary of these numbers. But now, today's mathematics, no problem. What is a complex number? We just think of, we expand our real line where we plot real numbers, the x. We expand it to a plane and say, let's just look at numbers which have both real and imaginary parts. And then they have operations of addition, multiplication, and so on. So in mathematics, it was all well developed. But what is perhaps surprising is that you could say, okay, so this is purely a product of imagination of mathematicians. But it turns out that this is complex numbers, imaginary numbers, and more general complex numbers are deeply woven into the fabric of the universe. In fact, our best theory for describing some subatomic particles, quantum mechanics, in quantum mechanics, these numbers are indispensable. It is based on complex numbers. And all this weird behavior that we learned, the double slit experiment, where you shoot electrons, through a wall which has only 2 slits, and you expect to have 2 bumps behind the slits, but in fact you are getting an interference pattern. This is all the signature. These are all the signatures of the fact that our universe has both real and imaginary numbers, you see. And so that's the kind of interference pattern I'm talking about. And so you see, it is numbers, you would never discover them though. A mathematician would never, or anyone would never discover them if we were to stay in the confines of what we think we know. Oh, we call them real numbers, so that's the real numbers, that's it, there's nothing else. Boom, and this way you block yourself, you limit yourself from discovering new vistas, new ideas, you see. And that's why Einstein was saying knowledge is limited, is always limited. There is always more. There's always something beyond what we know. My second example is a great Indian mathematician, Srinivasa Ramanujan. He was a genius who basically taught himself mathematics, came from a poor family in India, and then discovered some amazing formulas, for which we still don't have a proof, 100 years later, for some of them. Some have been proved, some haven't. He wrote to several people in England, mathematics professor, sent his formulas. And one of them luckily responded, G.H. Hardy. There's actually a great movie about this, which is called Man Who Knew Infinity. I don't know if you guys have seen it, but if you haven't, I highly recommend it. Great acting and great directing. Dev Patel as Ramanujan and Jeremy Irons as G.H. Hardy. A great, established kind of a dandy, Cambridge mathematician who embraced Ramanujan, who was able to understand and appreciate his ideas. And here's one of them, by the way. So how could anybody come up with this stuff, right? So if you do this sort of nested radical, Ramanujan discovered that this is equal to 3. So it looks like left-hand side, so complicated and cumbersome, but the answer turns out to be incredibly simple and straightforward. Right, so this is just one example of the mind of a genius. Like, oops, so G.H. Hardy said the following. He said about his discoveries. He said they must be true because if they were not true, no one would have had the imagination to invent them. I just love this quote because that's what is required. There is something which elusive, something which is beyond just simply memorizing, repeating, and so on. And this is, I think, such an important idea to convey to our students, you see. So, in fact, there is more, okay? So, well, I don't want to go all mystical on you, but Ramanujan actually said that he saw many of these formulas in his dreams. And there was a goddess involved, goddess Namagiri, who would appear and she would write formulas on the screen. It's such a beautiful, beautiful story. And she would write these integrals, and then he would wake up and write them down. And that's how he discovered many of these formulas. What do you make of that? Well, speaking of goddesses, I want to talk to you about another great mathematician, Sofia Kovalevskaya. She was a trailblazer, the first woman mathematician who received a doctorate degree, who became a professor at the university. This is all, believe it or not, this was just over 100 years ago, and she had to go through a lot of struggle to get to where she was. And her teacher, luckily, she had great teachers. But for instance, Weierstrass, who was one of her teachers, who was a professor in Germany, wanted to take her on as a student, but the rules were such that women were not allowed not only to enroll in the courses, but even to audit them, just over 100 years ago. And so finally, so basically had to meet her, she had to meet her professor in kind of clandestine fashion. But she was a brilliant student, and she made groundbreaking contributions to mathematics. She was also a prolific writer. And she only lived about only 40 years. So she died of tuberculosis, unfortunately, at a very young age. So just incredible, incredible, brilliant star. And so here is what she said. Said many people who never had a chance to know what mathematics is about, I think of it as basic arithmetic, consider it dry and fruitless subject. But in fact, it is a field that requires most of all, guess what's coming next, imagination. Mathematics requires most of all imagination. It is not possible to be a mathematician without being a poet at heart. It seems to me that a poet should see what others can't see deeper than others. And that's the job of a mathematician as well. So you see, what is it? What is it then? What is it? What are we talking about? Knowledge, we understand. Knowledge is, I have, lots of books behind me. You can't see them, but yeah, I'm surrounded by books here. And so, but what is it, imagination? What is it? What are we talking about? So Carl Jung, the great Swiss psychologist and the father of analytic psychology, who actually collaborated with scientists like Wolfgang Pauli and was one of the most brilliant minds of the 20th century. He wrote, imagination is a concentrated extract of life forces. A concentrated extract of life forces. The fifth element, right? So is this something? What is it? But when we talk about concentrated extract of life forces, I want to talk about one man who certainly possessed that kind of life force. Alexander Grothendieck, one of the greatest mathematicians of the 20th century, died about 6-7 years ago. So he revolutionized mathematics, one of the revolutionaries. So like Cardano, so suddenly, before that, only real numbers, suddenly you open up a new dimension. So that's kind of what Grothendieck did. He revolutionized algebraic geometry. And what exactly did he do? So I was thinking about this actually, as I was preparing last night. And you see, these imaginary numbers that we talked about, square root of -1, they are solutions of equations where the equation itself makes sense because it's built of real numbers. So here there's only 1 and 0. But the equation does not have solutions. So you can build equations out of what you know. But that equation may not have solutions in the realm or in the domain that you know. For instance, this equation has no solutions in real numbers, but it has solutions in imaginary numbers. In fact, there has 2 solutions, I, the square root of -1, and -5. This is just one of many of a huge archipelago of equations. So here's another familiar equation. If we think of this as an equation on 2 real numbers, x and y, then what this equation describes is a circle. In other words, solutions in real numbers give you a particular shape, geometric shape, a circle. But you don't have to be stuck in that domain, in that realm. You can go beyond real numbers and consider other complex numbers or other numerical systems. And it turns out that the same equation then would describe a completely different shape. So what, in other words, what it says is that equations are more important than solutions. You see, equations are more important than solutions, because when you talk about solutions, it means you already specify a certain realm, you specify a certain domain, and you restrict yourself inevitably. But if you just look at the equation, all possibilities are available to you. And that was the message, in some sense, from Grothendieck, you see. So, because he was able to take this to make a very elaborate mathematical theory out of this. So he came up with this notion of what we call today a scheme. That's a kind of a being, a kind of entity which lurks behind every equation. But that entity is not limited. It can have projections, expressions, solutions in different numerical systems. But it is one and the same equation, or one and the same scheme, we call it in mathematics. It's a kind of a conglomerate of a bunch of equations, one could say. It is not beholden to any of those masters, you see, any of those domains. Grothendieck also wrote that discovery is a privilege of a child who has no fear of being wrong once again, of looking like an idiot, of not being serious, of not doing things like everybody else. You know? I think that us, educators, we have to maybe remind ourselves of this quote, at least every few days, because when we teach our students, we can observe that life force. It can also be destructive, so it has to be contained in some sense, right? But it is such a gift that a child has, and that many of us, in some sense, it's not that we lose it, but it kind of dissipates because under the weight of knowledge, you see. And so where do we find this fine line between imparting knowledge on our children, but preserving that life force, So that's the question, that's the challenge. But it is essential to preserve it, because without it, we have just linear knowledge, and through linear knowledge. If we just focus on solutions, if we just force our students to memorize and give more emphasis, if we give too much emphasis on solutions, you see, that's what I'm trying to say. We are precisely cutting off that inspiration, that process of discovery. We are halting it, because then the focus is just on the solution. Then I can just memorize the formula. You see, it's on when you emphasize the equation and the process of the study of the investigation that you allow also that positive energy of imagination to come forth. So, well, here is a great Alexander Grothendieck as an old man on the right, and he is as a child. So I would venture a guess that it was that child inside that he preserved. He stayed with him, that was able to drive this groundbreaking discoveries, which we're still in awe of in mathematics today. So I also want to talk to you a little bit about a great logician, Kurt Gödel. Here he's shown with Albert Einstein. I started out with Einstein's quote. But Einstein said that they both worked in Princeton and at the Institute for Advanced Study. And Einstein used to say, the only reason why I go to work is that I could walk back home with Gödel. He thought Gödel was the smartest man. And he was, I think, in many ways. So Gödel is relevant to this discussion because as technology develops and as we get more and more, confined to all these little devices and become dependent on them, an idea inevitably arises that everything can be automated in the sense of computation algorithms, in the sense of mathematical formulas governing our lives. But what is left? What is there left then, if it's all a mathematical system, an algorithm, you see? And this is where Gödel tells us that actually there is more, that mathematics, in mathematics gives you very efficient tools to analyze and to derive new theorems, new equations from axioms and from old theorems and equations. It gives a beautiful structure, enables you to construct a beautiful structure. But it's not everything. For example, in any sophisticated formal system where you have axioms and rules of inference, like number theory or Euclidean geometry, there will be statements that are true but cannot be proved. So you cannot formalize truth, you see. You need something more. In other words, mathematics does not express absolute truth. And what I love about this especially is that here you have an example of a tradition. What is mathematics really? I mean, is it science? Is it art? A little bit of both, I would say. But it is a formal system. It is a certain structure. But it is a structure which is aware, it's a formalism, if you will, a conceptual system, okay? It is aware of its own limitations. Just think about this. It is aware of its own limitations. It knows that it cannot go out and say, this is the absolute truth. You cannot say that mathematics is absolute truth because mathematics itself, within mathematics itself, we can prove rigorously that that's not the case. A conceptual system, a formal system, aware of its own limitations. How many such formal systems do you know, by the way? This is the antidote, in my opinion, antidote to dogma. Because the danger is to start believing that there is this final theory, there is this final explanation, or worst of all, there is this one specific human being who possesses that, and that I now have to discard anything I know and just follow that guru, you know? The dangers of that are obvious. So the question is, what are the safeguards that we have? And the safeguard is, I would say, you focus on knowledge, make sure that the knowledge system, the conceptual system you follow is aware of its own limitations. Mathematics is because of Gödel's incompleteness theorem, you see. And that's why we appreciate mathematics so much. And this is such an important aspect which I think we must convey to our students to really to explain to them why mathematics is important. It's one of the most important aspects of it, in my opinion. So he wrote, the human mind infinitely surpasses the powers of any finite machine. So you see where I'm going with this. Knowledge, if everything was knowledge, you could entrust it to a computer, you could entrust it to a computational machine, because then everything would just be a linear process of absorbing more and more information. But human mind is capable of doing mathematics, and mathematics is not closed onto itself. That's the point of Gödel's theorem. And this is why he argued that a human mind infinitely surpasses the powers of any finite machine. It's exactly the statement that the process of discovery is not a linear process. There are discontinuities in it. There are jumps, insights, revelations. Remember Ramanujan seeing formulas in his dream. Where did they come from? Where do dreams come from? We don't know. The point is not to answer. Don't solve the equation. Don't solve it right away. Not yet, okay? Maybe we will solve later. But for now, how about just asking the question? How about just posing an equation, posing a question, and just contemplating it? That's the ability we have, which less and less utilized because of such a high pace of our lives today, because of the influence of technology, you see. But all these giants, you see, the ones on whom all this technology is based, or the ones on whose discoveries this technology is based, Einstein, Ramanujan, Cardano, Kovalevskaya, Gödel, look what they're all communicating to us. there is also imagination, there is also intuition. And never forget that there is something beyond the known, you see. And today, especially, I think a lot of my colleagues need to hear this, because, you know, we keep hearing about singularity and uploading one's mind, although perhaps less. When I spoke at METU, Middle East Technical University, back in 2015, that was very much on my mind. By the way, you could see that speech, that public lecture on YouTube. I was very concerned. I feel like today it's a little bit less so. So I think more people kind of awaken to the realization that all of this is, how to say, what's the a legal word for this, you know, kind of crap, you know. So in the sense that this idea that there is nothing to human being than being a human life is just a collection of zeros and ones, and a human being is just a bag of elementary particles, you know. That's just completely misses the point of the discoveries of science of the last 100 years. Science actually tells us that that's not the case. But there is a temptation. It is not by chance that there are such ideas, that they are in the public domain, and especially propagated by people who claim to be scientists, who claim to be to possess the necessary knowledge. Because there is a temptation, it's human nature, that if I know something, I feel a little bit superior, you know? I feel a little bit superior because I know, but nobody else knows. And then there is a temptation to use this, to use it as power, to use it to control, to manipulate. That's how our powers that be function. They use this, they use knowledge, or they use what we think we know, you see, to divide and conquer, and to control, and also to distract, and to make me focused on my on this device or on that device. But ultimately it doesn't work, because there is this other dimension which is not, how to say, it cannot be eliminated in this way, you see. This other dimension of this intuitive, fresh approach. There will always be, it will always be there, but it might become more and more difficult. That's true. And our children, this is where our responsibility as educators, in my opinion, comes, that we are not suffocating that dimension, and we not follow to, and not to do that, and to tell our students that here is a final theory, here is a grand theory that explains everything, and I have understood it, because see how nice, then I feel so good about myself that I understood it, nobody else does. This, by the way, in my opinion, is one of the reasons why our math education is in such a bad shape. It's because it's too tempting not to teach it well, because then it gives power to those who know. But that's hubris. That's why I put this word. I hope the translation. By the way, see, this is where I love, because on the one hand, technology gives. With one hand, it gives us so much. See, what is this? This is a screenshot from Google search, right? So Google not only was able to give me an explanation what this word means, but also translation to Turkish, which I hope is correct. So I'm not saying not to use technology, use it, but not allow yourself to be used by technology. So, you see, so that's the, and otherwise what happens? What happens? We know what happens. Actually, our great artists also have been on the case, and they have shown us very convincingly. One of my favorites in this regard is Stanley Kubrick's film 2001, A Space Odyssey, and this is a picture of HAL 9000. To me, HAL 9000 is that knowledge run amok. It's a left brain, it's a proverbial left brain, which have become so big that it is completely you know, occupied almost everything. So brings the humans to the brink. And finally, the captain, you know, David Bowman, he is Ulysses. He basically goes with a screwdriver and disables the computer. You see, that's that's the burst of his true nature, if you will, the burst of that life elixir that we talked about earlier. But yes, it is dangerous. And so, but also what is dangerous is the idea of that that there is a theory of everything, and we have to find it. And here, unfortunately, even some of the great popularizers of science, like Stephen Hawking, kind of send mixed signals. I'm not going to say that wrong signals, but mixed signals, because he spoke about how when we come up with this final theory, you know, we'll be able to understand the mind of God. This type of inflated rhetoric, in my opinion, is exactly a step in the wrong direction. It is exactly a step towards this idea that knowledge is everything, which precludes actually progress in science, as we have seen in the previous examples. So this is actually a wonderful quote from a recent review of a new book about Hawking, about Stephen Hawking. Now he doesn't, I'm not saying he doesn't bear the sort of responsibility for this. This unfortunately has been how we have taught our students, especially in physics, that we have to find this grand unified theory of everything, you know? They always have this, why do they always have this GUT, grand unified theory? Why can't it be just a unified theory, or a theory for that matter? It doesn't have to explain everything. Suffice it for it to explain something. This is where I have to say, mathematicians are a little bit, well, I think we are a little bit more aware of our limitations. And Gödel's incompleteness theorem is a great example for you of mathematics being aware of its own limitations. We never teach in mathematics classes our students that will come up with a complete theory of geometry or complete theory of number theory. No, we always say, whatever you do, there will still be open problems. But unfortunately, our physicist friends, sometimes they kind of go a little overboard. And this is where I like the admonition by James Gleick. He says, the theory of everything is a false idol. Why should the universe, which grows more gloriously complex the more we see, be reducible to one set of equations or formulae? The point of science is not the holy grail, but the quest, the searching and the asking, you see. This I completely agree. And this is where, by the way, when David Bowman in 2001, Space Odyssey, when he finally disables the computer, so in other words, disables his left brain, you know, this constantly thinking and acquiring information and knowledge, which may very well send you on a wrong track, which finally he disables. What happens? A star child is born. If you haven't seen the movie recently, I highly recommend it. It's very symbolic. So you see what happens. A child is born. And to remind you, the quote from a great mathematician, Grothendieck, discovery is a privilege of a child. No fear of being wrong, of being looking like an idiot, you see. So this is the thing. In our classrooms, yes, we have to have discipline, you know, obviously, and there has to be certain decor, but there's something to be said about that children possess this looking like an idiot. There is some quality to it, which is very positive. And it's important to remember that for us as educators, because that's the state you're in when you are on the verge of discovering something new, of going beyond the known. Carl Jung, whom I mentioned earlier, said, in every adult there lurks a child, an eternal child, something that is never completed and calls for unceasing attention. That's the part of human personality which wants to develop and become whole. To become whole. If we only focus on the knowledge and on imparting knowledge, it's lopsided, it's one-sided, it's not whole. It's one half of it, you see. There is more. So, and that's the challenge. Of course, we have to impart knowledge, and knowledge becomes more and more elaborate and requires more and more time and, you know, explanation and so on. And we have to do it. We'll have to do it while not suffocating the sense of awe and wonder and the sense of mystery. So I started out with a quote from Albert Einstein: "Imagination is more important than knowledge." And he also spoke about the mysterious. So this is a great contrast to me, because I think today, when we listen to some of our scientists, they are a little bit get a little bit ahead of themselves. All this talk about grand unified theory and so on that I mentioned earlier. But the great ones, you know, the great ones like Einstein, like Niels Bohr, the great scientists, they never lost sight of the mystery aspect, the unknown. And so, here's Einstein. By the way, there are many quotes attributed to Einstein, as you probably know, and sometimes they're not. He never said that. He never wrote this. But this actually is certified, a certified quote. The most beautiful thing we can experience is the mysterious. It is the source of all true art and science. He to whom the emotion is a stranger, who can no longer pause to wonder and stand wrapped in awe, is as good as dead. His eyes are closed. So our job as educators is not to allow this to happen to our students, that their eyes be closed. Our job is to preserve, to impart knowledge, but also to preserve that sense of wonder and awe and mystery. Luckily, we have our imagination. In addition to knowledge, we also have our imagination. This is our antidote to dogma and oppression. This is our way to survive and uphold our dignity. This is what we all have in common. It's what reminds us about our common goals and aspirations. This is what unites us. Dare to imagine. Thank you. This completes.
Okay, we have
the formal part of, and
okay,
I'm happy to take questions. Yes,
okay.
Please.
Mr. Ersin says, I, as a person from the field of foreign languages, German, was wondering what you think is the reason why the imagination normally expected of social scientists is mostly designed by mathematics, physics, or chemists.
I'm sorry, I couldn't hear the end of it.
Could you basically ask that, what do you think is the reason why the imagination normally expected of social scientists is mostly designed by mathematics, physics, and chemists?
What is imagination?
Normally expected of
what is
social
expected?
Is
what
not,
sort? Yes.
Wait a second.
Well,
I will send the question to you via chat box.
Oh yeah, maybe it's better because the sound is a little bit off. But in the meantime, I can also look in the chat and see if there are any questions here. Well, somebody says hello to California. Yes, hello from California. Yes, so. Oh yes, field of foreign languages, okay. What is the reason why imagination normally expected of social sciences designed by mathematicians? I'm not sure it's designed. So what I'm trying to say rather is it's natural. Imagination is natural. It's something, it's a natural ability, it's an innate ability that we have. It doesn't matter if we're in social sciences or in any kind of sciences. We use it every day, right? So even if we're not aware of it. And so we all dream, right? And so in that sense, but I focused in my talk on scientists, on the uses, so to speak, or the benefits of imagination in science, because I think it is a bit more. One can make a stronger case here in some sense, because one can make a stronger case because a sharper distinction between knowledge and imagination. So that's why, and also to see what the places, exactly the places of discontinuity of knowledge, where the development of the subject is non-linear, where there is a jump, discontinuity. For instance, you go from real numbers to imaginary numbers. How did this happen? It didn't happen by a monotonous, slow sort of grinding process. No, at some point somebody had to jump and depart from what was considered as a norm in the subject. Cardano said, let's consider imaginary numbers. So that's what I mean. That's what I mean. Okay, so each human has a chance of changing for each moment. That's right. I guess it's Viktor Frankl, right? So, and we learned to. I'm reading the questions in the chat. Is that okay?
Okay, it's okay.
So maybe that's. In universities, we learn to do certain things with the help of mathematics, of another infinite concept. But the things we learn, I told to us, it is the end. That's right. There is nothing behind it. Is it possible for something to be finite while the thing we used to learn is infinite? Exactly. Well, I would actually say the opposite, that what we are learning is infinite, and our knowledge at every moment is finite in some sense. So, so it is really, in the end, whether you believe in infinity. So as a mathematician, I like to phrase it in this way. But what is infinity? We have in mathematics a beautiful theory of infinity, which goes back to great German mathematician, Georg Cantor. By the way, Cantor also said the essence of mathematics lies in its freedom, which it also touches upon this other idea of freedom, that you don't actually have freedom if you are completely confined in the existing knowledge. And what he's saying is mathematics enables these jumps, like we saw in my talk. I give examples, and that's the essence of mathematics: this freedom, the freedom to change the numerical system. That suddenly you introduce new numbers into the game. You see, and so and this connects to what I said also earlier about dogma, and about how not to be trapped. And I sometimes wrote actually in my book Love and Math that. Where there is no freedom, where there is no mathematics, there is no freedom. That it goes both ways. So first of all, freedom is an essential quality of mathematics, as also of science as well in general. That you have to be free also to pursue within parameters of the subject, of course, right? But also, if you don't have proper mathematics education, then you are not free, because already you're denied the knowledge, so you don't even have a chance. Because if you don't even know what is known, you see, so what chance do you have to go beyond? So that's also an important aspect. Both are important, you see, and so, but it's infinite, and so that's the idea, that if you realize that the universe is infinite, or if there were all knowledge could be accumulated in one place, it would be infinite in all directions. So therefore, at every moment, you only have access to finite. That's why there is always something beyond what you know. That's why you're always open to it. Okay, next question. This I already answered. Okay, this I already answered. Okay. Okay, thank you. Mathematics is a key to life. Okay, great. I like this. Somebody writes that they were at my talk at METU as a student and didn't understand much at the time. Okay, now I'm here as a graduate master student and glad I could listen and understand me. Okay, well, thank you. I think I understand better also what I was saying 5 years ago. Thank you very much for your compliments, very positive comments. Sometimes we lose our motivation towards mathematics. What do you suggest? Can we use our imagination while traveling? Yes, exactly. So that's the mental tortures. Also, you see this quote from Cardano. Sometimes I know it for myself. I get too caught up in pushing in a certain direction, and in the end, what is it? It's trying to find the solution. It's trying to find the solution. When there is too much focus on finding the solution, then we kind of lose the big picture. Now, every once in a while, we have to do it. We have to find a solution. I'm not saying we shouldn't find a solution. Of course, we have to find it. And but this is where it's like a dream. So what did Ramanujan do? He would go to sleep, and in his dream, his goddess will come and show him a new equation, you see. So, okay, maybe not all of us can have access like this to VIP access, you know, to goddesses, but it's still inside. The goddess is inside, and that's our quest for knowledge, our quest for understanding and for new insights. And just remembering it, I think, is enough to not to lose interest, not to lose our motivation. Somebody else says imagination is enthusiasm to do things. That's right. No mathematics exists without enthusiasm. Yes, enthusiasm, but where does it come? Enthusiasm, it's innate, right? So it's something, by the way, not everybody has enthusiasm for mathematics, and I'm not suggesting that all students have to have this enthusiasm. But we have to allow this enthusiasm, if somebody does have it, not to suffocate it, and to actually amplify it. Or maybe to help somebody to discover this enthusiasm. Absolutely agree. Okay, well, cheers to Naples. Thank you for your comment. Truth. What is a truth? What is a truth? Well, in mathematics, truth is conceptualized in a particular way, that every statement can be also only true or not true. It's a particular valuation on the formal system or interpretation, you know. And so the statement of Gödel's theorem is that cannot be formalized without introducing additional axioms. There will be a statement which is neither proved, a true statement which is neither proved nor unproved in a true statement which cannot be proved neither this statement nor its negation can be proved. We can add it as an axiom, but then there will be other statements which cannot be reached in this way. Well, thank you very much. Thank you. Thank you. Infinite. Exactly. Possibility of classifying imagination as attainable and not attainable. Some concepts seem far-fetched, however, but by looking at them, could allow us to reach a more possible imagined structure. That's right. Yes, I agree. Yes. Thank you. I'm reading, so okay. I was wondering if you have any suggestion for middle school, high school mathematics teachers to inspire imagination for their students. Well, you know, that's a great question. I think that it's good to go a little bit beyond the curriculum, the standard curriculum of the subject, and to indicate other areas and indicate the big archipelago of mathematics, to show how vast the subject is, and to give examples of the type of mathematicians or discoveries that, for example, I mentioned today. For example, to talk to your students about Cardano, who he was, a fascinating story, life story, that he wrote this book, which was called The Grand Art of Rules of Algebra. That's just the name itself is inspiring, Grand Art, right? And so, and what did he do? And explain that he was undergoing mental tortures. And to say to your students, you're not the only ones. Even the great Cardano was undergoing mental tortures. We all do. And this brings the culture, kind of opens the doors. That's what I think the greatest thing that a teacher can do, apart from just teaching students, you know, specific theory and so on. But open those doors to this magical world out there. And it is accessible now more than ever because of technology, because you can go online and watch videos, for instance, on a Numberphile YouTube channel, which has millions of subscribers already. And I've done a bunch of videos for them, and it's really fascinating. Almost every week there's a new one. Or talk about Ramanujan. And now we have movies and we have books about all this great mathematician. And to emphasize those elements which are not traditionally emphasized in our mathematics classes, so that students don't feel trapped in this mindless pursuit of solutions. You know, to go back to my sort of the point I was making during my lecture, that the mindless pursuit of solutions is counterproductive. There are other interesting aspects to focus on in addition to looking for solutions. You see.
Sorry for interruption, but we have so less time and we have another speech after your speech. So
yes,
I have to finish now.
I think we have come to a good point, a good conclusion. So
yes.
I want to thank everybody one more time for being here and for your great questions and for your great attention. I wish I could be in front of you so I could see all of your faces, but I do feel the love and interest, and I really appreciate it very much.
We are also appreciated too, and participants, since you spare your valuable time to us. In addition to that, we planted a tree via Tema in behalf of your name as a thank you. Thank you for your speech. I hope we can be with you in the future events.
Yes, absolutely. With pleasure. Thank you very much.